Okay, well, to continue, we've just learned that smaller transistors are faster. Let's try to get some inkling of how very small transistors are made. So I'd like to talk about photolithography, okay? So hang on one second. Okay, this is going to be a very quick description, but we need to just have the basic idea. First of all, here's a crystal puller that might be used to make silicon ingots. Silicon crystals are pulled from a molten silicon, and it starts with a seed crystal. And if the seed crystal is pulled out very slowly under just the right conditions, the material will crystallize as it's pulled out of the melt and make a large single crystal of silicon, almost perfect crystal of silicon. Here are some silicon ingots of different diameters made through these kind of growth processes. Of course, the larger diameter you can make the crystals, the more material, the more area you have to make chips per crystal. Basically, the more money you can make per machine. So over time, the diameter of these crystals has grown and grown. People have learned how to make these crystal pullers larger and larger. Once the ingots are produced, they're sliced into wafers, which are polished to make these things here. And then the wafers are used the polished wafers are used in photolithography. So here, let's go through how this process works. So starting with a polished wafer, the wafer will be covered with photoresist. Photoresist is a chemical compound which is typically soluble in a solvent like acetone, but it's also photosensitive. And if it's exposed to ultraviolet light and baked, it will harden. And so the exposed portion will become insoluble, okay? So the wafer is covered with photoresist. And now we can do a trick. We can make a diagram, a reticule or a mask that lays out some of the circuit that we want to build on the silicon wafer. And then we can use photolithography. We can transfer that pattern to the silicon wafer by exposing the wafer with ultraviolet light through the mask and focusing an image of the mask onto the crystal. Then the wafer can be exposed to a solvent, acetone, and that will remove the photoresist from the areas that we don't want it, leaving behind photoresist in the areas that we do. We'll have transferred our pattern to the surface now. Okay, so we might end up in one little region with something like this. Okay. Now we can use the photoresist as a mask for an etching process. So here the wafer is etched. The photoresist itself blocks the etch. So the silicon is only etched in the regions that are exposed. Then the photoresist can be removed, and the pattern now is left behind on the silicon, okay? We can use this to do steps like the following. We can deposit a layer of material that's doped with a donor impurity, and then we can use photolithography to pattern that, and then we can remove the excess, and then we can heat up the wafer. And what that will do is to drive the donor atoms into the surface in the areas where they're present. And what will be left behind is a pattern on the surface that's like a pattern of conducting wires. Okay? We can also oxidize the surface and use photolithography to pattern the insulator, or to make a metal layer on the top that we pattern as well. Through multiple layers, through multiple photolithography steps, we can develop complex patterns on the surface that end up transferring the entire circuit that we want to build onto the surface. Okay? Then in the end, the material with all the layers that are required is finally done. The wafer is cut up into chips. The chips are packaged and they're ready to go. I think the current state of the art is 300 millimeter wafers. Okay? The entire wafer is developed at once and then it can be cut up into dozens or maybe hundreds of chips. In a modern fabrication facility, all of the steps I just showed you are all automated. So the machines are automated and the wafers are transferred between machines automatically to get reliability and, most importantly, to get cleanliness. It's very, very important that there be no contamination on the surface of the wafer, because when the circuits you're building are only a few dozen nanometers across, features, a grain of dust is enough to spoil an entire region. Okay? The cost of a state-of-the-art fabrication facility now is over $1 billion. So this is not a cheap undertaking, okay? For state-of-the-art production. On the other hand, research labs use much smaller wafers and smaller processing and use manual equipment at a much lower cost. Okay, here, let's pause for a second. Oh my gosh. Okay, well, here, now I wanted to show you this graph. This is one of the most famous examples of exponential growth around. It shows the number of transistors per die, roughly the number per chip, manufactured at different times. So starting in 1971, up till the present day. Well, this graph only goes till 2019. But what one sees is that the number of, and notice that the y-axis is logarithmic, that the number of transistors per die has grown exponentially. The data look like a straight line on a log linear graph, okay, over this entire period. Starting from a few thousand transistors per chip in 1971 to now hundreds of billions of transistors per chip. There are different types of chips shown here. Memory chips, these are the upper branch here, have the are the densest kind of integrated circuits built, because for a memory chip, all you really want is to pack a lot of a lot of storage into the smallest possible space. So here, making small transistors is an absolute premium. The other branches are other types of devices, in particular, logic chips, processing units, where there are other concerns besides just sheer size. The data that I'm showing you here embodies what's called Moore's law. The number of transistors per chip doubles every 2 years. And so over this stretch of time, 30, almost 50 years, more than 40 years, almost 50 years, the number of transistors on a chip has been doubling every 2 years. Now, obviously, this kind of growth can't go on forever, but there's no clear idea at the moment when it might stop. So that's something interesting to think about, okay? Okay, well here, let's take a look at some of the limits to scaling transistors, shall we? Okay, there are 3 that I want to talk about. The first, and maybe the most obvious, and perhaps the most important, are the limits to photolithography. Okay? Very briefly, the wavelength of light limits the smallest features that we can make. Oops. If we use a microscope to focus light, Oh my gosh, 1 second. Then what we find is that, of course, the size of the focal spot can't be infinitesimally small. In fact, the radius of the focal spot, the resolution of the lens, if you like, is often written as lambda over 2n sine theta. So in this formula, lambda is the wavelength of the light. Theta is the convergence angle of the rays here. So having the light focus very sharply is better than having it focus over a narrow cone. And then n is the index of refraction of the medium in which we're doing the focusing. And that occurs really because the wavelength in the medium is really lambda naught over m. In any event, so this, of course, is a fundamental limit. The second one, I'll call process variation. And it just is telling us that because the world is made up of atoms, for example, because my donor ions are each individual atoms, oh my gosh, this is just not going to work. Because of that, something weird happens when the device gets very small. For example, in our FET transistor, shown here schematically, the threshold voltage is given by the free charge in the channel divided by the capacitance of the gate and channel together. But the free charge in the channel is given by the density of donor ions times the volume of the channel times E, okay? And if the volume gets very small, then something weird will happen. So, for example, if our channel was, let's say, 20 nanometers cubed, so imagine a cube 20 by 20 by 20, okay? This would be about 10 to the minus 23 meters cubed. So then if the donor density is about 10 to the 24 atoms per cubic meter, then that means it will have about 10 donor atoms in the channel. So 10 free electrons, that's how many free electrons we'll have in the channel. And the problem with that is that, well, you know, these donor ions, they end up there randomly. We just add some donor impurities to the mix, and then they sort of randomly work out. So that means if we try to make these, sometimes we'll have 10 atoms in the channel, but sometimes we'll have 8, and sometimes we'll have 12. There'll be a random fluctuation, which will be relatively large because of the statistics of small numbers. So, and because of that, the threshold voltage will vary a lot from device to device, okay? There's no way around this really, because there's no way to control the number of donor ions in our channel with a precision of greater than 1. We can illustrate the third with the same drawing. Of course, there are processes that can only occur when things get very small. And one of them is quantum mechanical tunneling. We can have, in a very small device, we can have tunneling between the gate and the channel, or between the source and the drain, so that the following can happen. Gate channel current is just a kind of leakage It means that the device consumes current all the time, as would source drain tunneling. So in this case, even when the transistor was off, it would still draw some current, and the contrast between off and on would not be very large. So tunneling produces leakage current, and leakage current produces heat. Okay? And too much heat will eventually destroy our device. Of course, tunneling is the worst kind of problem because it gets worse and worse exponentially as our devices get smaller and smaller. Okay? All right. Well, now let's try to see what people have done to try to overcome these limits so far. Okay, so how have people tried to overcome the limits to scaling, and what's allowed this progress to occur over all these years? So first of all, the most obvious problem to overcome is the lithography limit. So the limit to resolution are the following. We can make the feature size smaller and smaller as long as we can keep using smaller and smaller wavelengths. And that's what people have done. So this shows over a span of time from 1985 to the present, the different light sources that have been used in photolithography. So these are all ultraviolet light. But we start out with 365 nanometer radiation, and using this to make devices on the order of 500 to 1,000 nanometers. And then here you have 248 nanometer light, 193 nanometer light. We've gone further. Photolithography has shifted to light sources further and further into the ultraviolet. In the around 2010, people were using 193 nanometer light, but using it in immersion, meaning that the lenses and the wafer and all the optics were immersed in ultra pure water, in order so that the wavelength of the light in the water would be smaller by a factor of the index of refraction of water. Most recently, in the last 5 years, there's been a big revolution. People have shifted to using extreme ultraviolet light, almost X-rays really, with wavelengths of 13.5 nanometers. This is really an amazing process. It's an amazing feat of technology. If you'd like to learn a little bit more about it, you might watch this YouTube video here, okay? But this process has been developed and machines are sold by a company called ASML, which is based in the Netherlands. I think each machine costs something like over $100 million. There are a few hundred of these in the world. Half of them belong to TSMC, Taiwan Semiconductor Manufacturing Company. And so now Apple Computer and many of the other high-end American computer companies are getting all of their chips, all of their high-end chips from Taiwan, from TSMC. Okay. Okay. Well, what kind of structures then can you make with these very short wavelengths? And how can you try to overcome the problems that we've talked about, the problems of tunneling and process variation? So another change that's occurred over the last 20 years is that technology has shifted from planar FETs, like the ones that we've used in our examples, to what are called FinFETs. In a FinFET, the channel is a narrow fin, and the gate almost completely surrounds it, as shown here. This way, when you deplete the channel by applying a voltage to the gate, the channel is depleted on 3 sides. Zonk. And it really suppresses things like tunneling. Okay, here's an image of an electron microscope image of a FinFET. Here's the fin, and here's the gate electrode that almost completely surrounds it. Here's some more cartoon pictures of a planar FET, the FinFET, and now even more confined kind of design called gate all around. Now the gate is a narrow wire, a nanowire, which is surrounded on all sides by the gate. Okay. Here's another SEM image of a FinFET. So there's been a change in the geometry of FETs to make them smaller, but also to make them less susceptible to things like gate leakage. Okay. In this way, Moore's law has been extended for another another 20 years. If you, I'm sorry, I'm going to just jump back to that for 1 second. Okay, well, that brings us back to this plot. Okay, so these recent advances have managed to push Moore's law further forward, but it's always an open question how much longer this kind of exponential growth can continue. In fact, if we look more closely, you can see some issues cropping up. The next graph shows not just transistors per die over time, but here's the operating frequency. The frequency, the clock frequency in chips, has actually stagnated since about 2005. So remember we said that smaller was faster? Well, that's no longer true. Now, smaller is no longer faster. The speed is kind of fixed. The reason is because smaller means more power, and more power means because more switching operations per second, each one embodying a certain amount of energy that has to be dissipated from each transistor. And more power means more heating, and more heating, well, there's a limit to how much power you can dissipate from the integrated circuits. You can see that here too. The amount of power consumed by an integrated circuit has also plateaued because there's no way to operate the semiconductors if you let them dissipate too much heat and get too hot. Okay? So in fact, besides getting smaller, the most important thing that's happening now is that the complexity of computers is growing instead. So instead of just making things smaller and smaller, we can make computers more powerful by increasing the number of processor cores instead. Finally, because the cost of the equipment to make smaller and smaller transistors is going up so fast, now over $1 billion for a fabrication facility. The fact is that now smaller is no longer cheaper. So over the past few, in the past recent history, as the process size has gotten smaller and smaller, the cost per transistor no longer goes down. So they're no longer cheaper or faster or lower power as you make them smaller and smaller. But it's still true that you can fit more processing power into a small package, which is still very important for the makers of the highest end electronics. So for now, the motivation for Moore's law is still there, and apparently the technological wizardry to keep making things smaller is still there as well. By the way, I'll say one more thing just before we quit. You'll notice that this process size is 7 nanometers. And if you look on the web, you'll see that the current process size I think is 7 nanometers or 5 nanometers, which seems to be below the resolution limit of 13.5 nanometers. So I just want to warn you something about these numbers. It used to be that these numbers were the size of the smallest feature on the semiconductor chip. That's no longer true. Now, these are just markers. Every 2 years, Moore's law says that you should be able to double the number of transistors, and people have doubled the number of transistors. And so they just call that process size the next smaller process size. So if you double the number of transistors, then the label that gets attached is one that's smaller by a factor of square root of 2. But the smallest features are not actually 7 nanometers or 5 nanometers. They're much larger than that. Those are just the labels that are attached. Okay, but definitely it's still true that Moore's law, number of transistors per chip, is continuing to double every 2 years. Let's stop here.